Have you ever wondered how engineers manage to build structures under the vast oceans and rivers? This question may have crossed your mind at some point, sparking an interest in the remarkable field of engineering known as underwater construction. This sector is about as complex and intricate as engineering gets. It's a fascinating discipline that dares to venture where few others do, plunging deep the water's surface to create structures that defy nature and leave us in awe. When we talk about underwater construction, we're referring to a type of engineering that focuses specifically on creating structures below water level. It's a task that is as challenging as it is intriguing. The thought of dealing with elements such as gravity, structural stability, water pressure, currents, and various environmental factors is enough to make even the most experienced engineers raise their eyebrows. It's a daunting task, but one that has borne fruits that are integral to our daily existence. In the grand scheme of the world's infrastructure, these underwater constructions play critical roles. They serve a multitude of purposes and have become so ingrained in our everyday lives that we often overlook their importance. A closer look, however, unveils a world filled with marvels that underline human perseverance, creativity, and the sheer power of engineering. Now let's take a moment to consider some of these underwater constructions. First and foremost, we have offshore oil. These colossal structures are marvels of engineering that contribute significantly to the world's oil supply. With their towering frames standing tall amidst the rough ocean waves, these behemoths drill deep into the seabed to extract crude oil. Their design and construction require the utmost attention to detail, as they must withstand the harsh oceanic conditions while performing their critical function. Then, we have bridges, tunnels, infrastructure that represents true marvels of engineering. They are a testament to our insatiable desire to connect and explore, linking lands separated by vast bodies of water. Built to carry heavy traffic and resist the erosive powers of water, these structures require a fine blend of design ingenuity, solid construction principles, and top-notch materials. Another intriguing part of underwater construction is the creation of ports. These are not just simple docking points for ships, but complex structures serving as vital hubs for global trade. Goods from every corner of the globe pass through these ports daily, making them essential components of the global economy. They need to be robust, designed to accommodate large vessels and withstand the forces exerted by tides and waves. Beyond these, we have pipelines, the silent heroes of underwater construction. Often unnoticed, these pipelines crisscross the ocean floor, transporting oil, gas, and even water from one to another, often across vast distances. These underwater feats of engineering ensure the smooth running of industries and households across the world, making life as we know it possible. Underwater construction is a field of engineering that's deeply intertwined with our daily lives, even if we don't always recognize it. These structures, from the smallest pipeline to the largest oil rig, stand as powerful symbols of human intelligence, creativity, and the relentless pursuit of progress. They are testaments to our understanding of marine environments, material science, and construction techniques. In essence, these structures are a testament to human ingenuity and the power of engineering. They remind us how far we've and how much further we can go. It's a fascinating realm filled with challenges and rewards, demanding a deep understanding of various sciences and techniques. To understand this fascinating process, we'll dive deep into the world of underwater construction. So fasten your seatbelts and join us on this exciting journey into the depths of the sea to unravel the mysteries of underwater engineering. Every great construction begins with meticulous planning and design, and underwater construction is no exception. The beginning of such a project is always identified by a comprehensive examination of the location's environmental conditions. To conduct a thorough assessment, seasoned engineers plunge into a sea of information, meticulously scrutinizing factors such as water depth, currents, wave action, the composition of the seabed soil, and the topography of the ocean floor. An understanding of these parameters is not only beneficial but vital, as they significantly steer the design and construction course of any underwater structure. One prominent example is water depth. This factor directly impacts the pressure conditions that both the structure and the divers involved in the construction process will have to endure. An increased water depth translates to increased pressure, creating a challenging environment for both divers and the structure itself. Engineers must therefore devise construction strategies that take this into account, ensuring the safety of the divers and the longevity of the structure. The role of currents and wave action in this process cannot be overstated. These elements play an instrumental role in determining the stability requirements of any structure being built underwater. Strong currents and wave action can introduce significant instability, requiring specialized construction methods and equipment to ensure that the structure remains secure. Furthermore, these factors also influence the choice of construction methodologies, as strong currents can pose substantial challenges to divers and equipment alike. Overcoming these hurdles often requires innovative thinking and sophisticated engineering solutions. Next in line is the composition of the soil and the topography of the seabed, which are equally important parameters in the planning process. These factors fundamentally determine the foundation design of the structure. For example, building on a rocky seabed might necessitate a different approach compared to a sandy or a muddy one. Understanding the intricacies of the seabed's contours can assist engineers in identifying potential challenges, such as slopes, valleys, or depressions, that complicate the construction process. Beyond understanding the environment, engineers must also consider the purpose of the structure being built. Is it an offshore oil rig tasked with extracting vital fossil fuels? A bridge aiming to connect two separate land masses? A tunnel designed to run beneath a bustling waterway? A port destined to serve as a hub of maritime trade? Or a pipeline built to transport essential resources? Each of these structures has unique requirements and constraints, significantly influencing the design process. Take an oil rig, for instance. It needs to withstand not just the harsh marine environment, but also the stresses and strains of drilling operations. Its design must accommodate for the vibrations generated by drilling, the corrosive effects of seawater, and the potential risks of oil leaks. A tunnel, on the other hand, presents a different set of challenges. It has to be watertight, capable of enduring the pressures of the water above and the traffic within. Its design must account for potential leaks, ensure structural integrity, and provide for emergency exits and ventilation. Regardless of the structure's purpose, the goal of engineers is to create designs that the right balance between functionality, durability, safety, and cost-effectiveness. Harnessing the power of sophisticated software tools and their deep understanding of marine environments, materials, science, and construction techniques, they meticulously craft these designs. They consider every possible scenario, prepare for all eventualities, and ensure that the structure they design can withstand the test of time and nature. Their work does not end with the design. They also oversee the construction process, ensuring that every aspect of their design is accurately implemented and that all potential issues are swiftly addressed. With a comprehensive plan and design in place, the next step is to prepare the site. Preparing the site underwater is an intricate process, yet crucial for the success of the project. Envision this task as a complex dance. It's a ballet of engineering, a choreography between man, machine, and nature, all collaborating in unison to create a stage for the upcoming construction. This task is a feat that requires unparalleled precision, skill, and the meeting of minds between different experts. It is a multifaceted process, with each of preparation as critical as the next. The underwater construction process begins with the act of dredging. Dredging is the initial stage of clearing the site, akin to a deep clean. This process involves ridding the site of sediment and debris that have accumulated over the years. Think of it like vacuuming your living room before rearranging furniture. However, instead of using a simple vacuum cleaner, dredging requires the use of heavy machinery. These robust machines often operate from a barge or a specialized dredging vessel. The process of dredging is more than just cleaning. It aims to ensure a clear and unobstructed space, setting the stage for the next steps in the construction process. Each grain of sediment removed, each of debris cleared away, contributes to creating an ideal workspace. It is a meticulous task that requires patience, precision, and a deep understanding of underwater terrain. Once the dredging process is complete, the seabed must be leveled. Leveling the seabed is not a task to be taken lightly. Picture yourself trying to level a sandcastle, but underwater. The challenge is compounded by the currents and waves that constantly shift the sand around. This is when engineers step in, using their expertise and knowledge to create a leveled seabed. The process of seabed leveling is a complex one. It's not just about making it flat. It involves creating a solid, sturdy foundation that can withstand the significant weight of the structure that's about to be built. These engineers play with the elements, manipulating the seabed and using their expertise to ensure the area is suitable for construction. It's a fascinating blend of science, art, and ingenuity. With a clean and level site, we're ready for one of the most thrilling parts of underwater site preparation: the installation of temporary structures. These structures, like cofferdams or caissons, play an essential role in creating a dry workspace underwater. Think of it as a protective bubble or shell, a barrier that keeps the water at bay, while allowing engineers and construction divers to perform their tasks as if they were on dry land. The creation of these structures is an awe-inspiring accomplishment of engineering. It's a testament to human ingenuity and tenacity, a demonstration of how far we have come in our understanding and manipulation of our environment. Each piece installed, each bolt tightened, is a step closer to having a completely safe and secure underwater workspace. So there you have it, a detailed journey through the underwater ballet of site preparation. It's a dance of precision, a symphony of expert choreography and perfect timing. From the initial dredging to the meticulous leveling of the seabed, to the installation of temporary structures, each phase is critical. Every decision, every move is calculated with the utmost precision, ensuring the success of the project. Once the site is ready, the real construction begins. But don't forget, the stage upon which this construction will take place is not just any stage. It's a stage that has been painstakingly prepared, situated deep under the sea, primed to facilitate the marvels of underwater construction. Every grain of sand, every piece of machinery, every temporary structure contributes to creating a platform ready to support the wonders that will soon be built upon it. It's the result of tireless work, relentless determination, and undying dedication to achieving the seemingly impossible. Underwater construction employs a variety of techniques tailored to the unique challenges of the marine environment. The exploration of the ocean, even up until recently, remains vastly incomplete. With its vast expanse, the marine environment presents unprecedented opportunities for exploration, innovation, and construction. Various techniques and methodologies are implemented to meet the unique challenges of this environment, making underwater construction a field of special interest for engineers, architects, and researchers. The fascinating world of underwater engineering hosts a multitude of techniques and methods, which in the grand scheme, each play their part in the successful construction of underwater structures. From employing human skill and dexterity to utilizing high-tech machinery and materials, this field blends the best of human capability with technological advancement. Firstly, we have the construction divers, the unsung heroes of underwater construction. These professionals are not just divers, they are equally skilled in the fundamental aspects of construction. Their training encapsulates a comprehensive understanding of the principles of construction along with the techniques of diving. They operate with precision under the water surface, performing intricate tasks that are critical to the success of the construction project. The work of a construction diver is not for the faint-hearted. Their role is physically demanding, and they often work in challenging conditions. They have to constantly contend with factors like water currents, visibility, and pressure. Their equipment comprises specialized tools such as underwater welding torches, cutting tools, and hydraulic machinery. These tools enable them to perform their tasks efficiently, whether it's joining metal pieces together, shaping structures, or carrying out heavy-duty tasks. Consequently, the dedication and skill of a construction diver are fundamental to the success of every underwater construction project. Next is the incorporation of remote-operated vehicles, or ROVs. These advanced machines have revolutionized underwater construction. They are unmanned, remote-controlled machines equipped with cameras, manipulator arms, and a variety of other tools designed to perform specific tasks. ROVs contribute largely to underwater construction when it's not feasible or safe for divers to work. This includes conditions such as extreme depths, strong currents, or hazardous environments where human intervention would be risky. They can perform tasks remotely, such as inspecting underwater structures, laying cables, or even collecting samples from the seabed. Their use has made underwater construction safer and more efficient. Another key technique in underwater construction is the use of prefabricated components. These components are built on shore in a controlled environment and then transported to the actual construction site for assembly. This technique offers multiple advantages. It streamlines the construction process, saving a considerable amount of time. Not only can multiple components be built simultaneously, but the controlled environment in which they are built also ensures a higher degree of quality control. Once the components are transported to the site, divers or ROVs assemble them, giving shape to the final structure. The next critical technique in underwater construction is concrete placement. This process is far more challenging underwater than on land. It involves special techniques to prevent concrete washout, where the cement is swept away by water before it can harden and cure properly. One commonly used method is the use of tremie pipes. Long and narrow, these tubes directly deliver concrete to the desired location, ensuring that the concrete remains unaffected by water currents. This method is highly effective in creating a strong, sturdy base for the structure. Underwater construction, in essence, is a fascinating blend of engineering, technology, and human skill. The techniques we've discussed, from the hands-on work of construction divers, the technological prowess of ROVs, the efficiency of prefabricated components, to the precision of concrete placement, all play pivotal roles in bringing underwater structures to life. However, the story doesn't end here. Alongside these techniques, the choice of construction materials is equally important. Materials must be carefully selected to withstand the harsh marine environment, including corrosion from saltwater and biological degradation. But that's a topic for our next section. Stay tuned as we delve deeper into the world of underwater construction. In the harsh marine environment, not just any material will do. This statement might sound simple, but in reality, it's a significant challenge in the field of underwater construction. The marine sphere is a harsh and unforgiving place. The selection of construction materials for underwater projects is not only important, it's absolutely crucial. It's as vital as the design and impeccable construction techniques themselves. You must understand that the chosen materials should withstand the extreme elements that the marine environment throws at them. They must bear not just the immense pressure and dramatic temperature variations, but they also need to confront the highly corrosive effects of salt water. Addition, the relentless process of biological degradation is another factor that the materials should resist. Imagine the materials being gnawed away over time by undersea life, eroding their strength and durability. It's a grim picture, isn't it? However, in the face of these daunting challenges, some materials have emerged as the unsung heroes of the underwater construction world. We're going to delve deeper into these champions. First up, we have the popular and widely used material, concrete. It's a favored choice in marine construction due to its impressive durability and resistance to water. But let me clarify something here. The concrete used in underwater construction is not your everyday, run-of-the-mill concrete. It's a much more specialized form. For underwater applications, concrete is often mixed meticulously with various additives. These additives are meant to enhance its overall strength and significantly reduce its permeability, making it what some might call super concrete. And to ensure that this super concrete sets properly without being washed away by the relentless water currents, it is placed using innovative techniques like tremie pipes. Next up to bat is the ever-dependable material, steel. Known far and wide for its exceptional strength and versatility, steel is a common ingredient used in the construction of underwater structures. But like most things, steel has an Achilles heel: corrosion. Despite being robust, the resistance of steel towards corrosion is its weak. To combat this, engineers and inventors have come up with ingenious methods. They often use corrosion-resistant alloys or even apply protective coatings to steel. These measures help to transform steel's Achilles heel of corrosion into a strength, enhancing its usability and prolonging its lifespan in the construction of underwater structures. Another material that has found favor in the realm of underwater is fiberglass. Why, you ask? Well, fiberglass is lightweight yet sturdy, resistant to corrosion, and it holds a high strength-to-weight ratio. All these qualities make it perfect for applications where weight is a significant concern. And lest we forget another important material, corrosion-resistant alloys. They're typically composed of various elements like nickel, chromium, molybdenum, and others. These alloys are engineered with the express purpose to resist the corrosive effects of salt water. These materials are used in the construction of critical components that require high strength and durability. It's a delicate dance, choosing the right materials for underwater construction. Each material comes bearing its own set of strengths and weaknesses. Engineers must balance these aspects, keeping in mind the unique demands of the project and the environmental conditions. This process is not unlike a complex ballet, where getting the right steps in is critical. With the right materials and techniques, the next focus is ensuring the structure's integrity. It's a challenging task that requires the perfect blend of science, engineering, and a dash of creativity. And that, dear listeners, is a tale for another time. The safety and longevity of underwater structures hinge on their structural integrity. This sentence possesses an undeniable truth in the world of underwater construction, a field that revolves around the principles of stability and sustainability. But what does it mean, and how do engineers ensure this integrity? To understand this, we need to dive into the world of underwater construction, its rigorous inspections, and innovative testing methods. Upon the completion of the first step in ensuring the structural integrity of these underwater behemoths is a thorough inspection. This is similar to a doctor conducting a comprehensive physical examination. The professionals meticulously scrutinize every inch, every nook, every cranny of the structure for any potential flaws, imperfections, or weaknesses. This visual inspection ensures that every part, every bolt, every weld is in optimal condition, ready to withstand the ocean's relentless onslaught. But visual inspection is simply the tip of the iceberg. Engineers also harness the power of a technique known as non-destructive testing, or NDT. As the name eloquently suggests, NDT enables us to test the structure without inducing any. It is a technological marvel that enables us to peer beneath the surface, to uncover and understand any hidden issues that might have escaped a visual inspection. Non-destructive testing comprises numerous methods, each with its unique benefits. One such popular method is ultrasonic testing. This ingenious method utilizes high-frequency sound waves to detect any flaws within the materials used. It can be likened to an ultrasound for buildings, laying bare what's concealed beneath the outward surface. It's a crucial tool for engineers, acting as their unseen eyes, exploring the depths inaccessible to the naked human eye. Another highly effective method within the NDT arsenal is magnetic particle testing. This technique is particularly proficient in revealing cracks or discontinuities on or near the surface of ferromagnetic materials, such as certain types of steel. It is like an X-ray machine for materials, revealing any potential weaknesses. But the challenge does not end here. What about the parts of the structure that are hidden below the seabed, far from the prying eyes of engineers? How can their integrity be ensured? This is where underwater sonar imaging comes into play. Sonar, an acronym for sound navigation and ranging, employs sound waves to chart the underwater. It functions akin to an echolocation system for engineers, providing a detailed snapshot of the structure's unseen foundation and the surrounding seabed. This triumvirate of visual inspection, non-destructive testing, and sonar imaging provides a comprehensive assessment of the structure's integrity. It empowers engineers to identify and tackle any potential issues, ensuring the structure's strength and stability. Nevertheless, the testing regimen does not conclude here. Following the initial checks, the structure is subjected to a sequence of load tests. These tests mimic the stresses and pressures the structure will confront throughout its operational life, from the weight of vehicles on a bridge to the force of relentless waves on an offshore oil rig. Akin to a stress test for buildings, pushing them to their limits to ensure they can bear the rigors of their harsh environment. Finally, the structure is monitored round the clock throughout its operational life. An array of sensors embedded deep within the structure furnish engineers with real-time data on its performance. These sensors act as silent sentinels, allowing engineers to detect and address any issues that crop up over time. Through this relentless cycle of rigorous testing and continuous monitoring, engineers ensure the structural integrity of underwater constructions. It's a meticulous and ongoing process, a testament to human ingenuity and our relentless quest for safety. While structural integrity is vital, so too is the environmental of these projects. This is a topic we'll unravel next time, as we continue our exploration of the environmental considerations in underwater construction. Underwater construction doesn't occur in isolation. It interacts with delicate marine ecosystems. This relationship necessitates an obligation for comprehensive understanding and meticulous planning to minimize potential environmental impacts. When we delve into the topic of underwater construction, we are engaging with a sphere that serves as a home to a wide array of marine and fragile ecosystems. These ecosystems are inherently sensitive to any disturbances, and their well-being directly shapes the health of our planet, forming a significant portion of our blue planet's life support system. When we ponder about the planning stages of any underwater project, whether it may be an oil rig or a submarine cable, a comprehensive environmental impact assessment is conducted. This systematic process assists in predicting the environmental consequences of a proposed project. It helps to ensure that the potentials for significant environmental effects are identified and assessed early in the decision-making process. The key goal here is to identify any potential risks to the marine environment and devise action plans to mitigate them effectively. One of the most recurring concerns is the disturbance of the seabed. Construction activities, with their heavy machinery and intensive operations, can inadvertently stir up sediment, which can blanket marine life and disrupt the delicate balance of the ecosystem. To minimize this inevitable disturbance, engineers employ innovative techniques such as silt curtains, are specially made curtains that effectively contain and control the spread of sediment, preventing it from dispersing into the surrounding water and causing harm. Another pivotal consideration is noise pollution. Contrary to popular belief, the underwater world is a surprisingly environment, with sounds from waves, marine animals, and even seismic activity. Additional noise from construction activities can disrupt marine life, especially species that rely on sound for communication, foraging, and navigation. To address this, engineers may strategically schedule construction activities during times when they are least likely to affect sensitive species, thereby causing minimal disruption to the natural behavior and life cycles of these animals. Protecting endangered species is yet another paramount priority. If a project is located in an area to be inhabited by endangered species, engineers must take extra precautions. These could include meticulously adjusting the timing of the project to avoid critical periods such as breeding and feeding seasons. Another strategy could be implementing exclusion zones, which are specifically designated areas that exclude certain activities to keep these species away from the construction site. This ensures the survival and well-being of these species, even amidst the construction activities. Pollution prevention is another crucial aspect that must be considered. Measures are put in place to prevent leaks or spills of harmful substances into the water. This could involve using environmentally friendly materials and fuels that are less harmful to the marine environment. It could also include installing containment barriers designed to catch any accidental, thereby preventing potentially hazardous substances from contaminating the water and harming marine life. Lastly, let's talk about waste management. All waste generated during construction must be responsibly managed and properly disposed to prevent any debris from entering the marine environment. This encompasses everything from construction debris to daily waste from workers. The proper management of waste is crucial to ensuring that our oceans remain clean and our marine life is protected. The responsibility of engineers extends beyond construction, to include regular maintenance and repair. This ongoing commitment ensures the long-term sustainability of underwater structures while also protecting our precious marine ecosystems for generations to come. This is a multifaceted effort that requires the collaboration of all stakeholders, from engineers and construction workers to policymakers and environmental activists. It is our collective responsibility to ensure that our marine ecosystems remain healthy and vibrant for future generations to enjoy and appreciate. Like any other structure, those built underwater need regular attention to remain functional and safe. Similar to how we ensure the smooth functioning of our vehicles through regular oil changes, replacements, brake audits, and tire rotations, underwater structures necessitate their own unique care. If neglected, much like an unmaintained car breaking down in the middle of the road, these essential structures could falter, presenting significant risks. Therefore, the maintenance of underwater structures is a continual process, requiring consistent effort, time, and resources. The first pillar of this maintenance process is the periodic inspection of these structures, akin to the routine checkups we undergo at the doctor's office. Just as a general health check can catch minor health issues before they escalate into grave conditions, these inspections perform a similar task for the structures. Regular surveillance of these structures may reveal signs of corrosion, structural damage, or other anomalies that require attention. A small crack in the structure's surface, if left unattended, can grow into a significant defect, jeopardizing the structure's stability and safety. Corrosion protection forms another crucial aspect of maintenance, specifically tailored for these underwater structures. Remember, these structures are in a continuous war with the saline seawater, an infamous adversary of materials like steel. The relentless saltwater attacks the metal, causing it to rust and weaken, compromising the structure's integrity. To counteract this, various corrosion protection measures are employed. One such method of protection is cathodic protection, where a sacrificial metal is introduced to the structure. This metal, often zinc or aluminum, is more reactive and draws the corrosive elements present in the seawater from the structure. In doing so, It sacrifices itself and spares the structure from corrosion, very much like a knight taking a blow intended for his king. Another popular method of corrosion protection is the use of protective coatings or paints, which serve as a barrier between the structure and its corrosive environment. These coatings, much like a shield in battle, protect the structure from the onslaught of corrosive elements in the seawater. In addition, structural reinforcements play a pivotal role in maintaining the longevity of these underwater structures. Over time, the unyielding forces of ocean currents, waves, action, and even marine life can compromise the structure's integrity. To combat this, reinforcements can be added in various forms, such as additional support beams or even the use of fiber-reinforced polymers. The repairs, when deemed necessary, are equally demanding and complex. They often require specialized divers or remotely operated vehicles, ROVs, to carry out intricate tasks under challenging conditions. These tasks might include welding underwater, replacing damaged parts, or adding further reinforcements. Importance of prompt and effective repair work cannot be understated, as minor problems can quickly escalate into major ones if left unaddressed. Maintenance and repairs of underwater are not just about keeping these structures functional, they're also about ensuring safety and sustainability. These structures, whether they're oil rigs, bridges, or pipelines, often play critical roles in our daily lives. Their well-being directly impacts ours, and the economies, as a breakdown could lead to significant losses and potential environmental disasters. If maintained effectively, these structures can serve us for decades, contributing to our lives in ways we may not always appreciate. They deliver our energy, facilitate our transportation, and even provide platforms for scientific research. Their maintenance is thus an essential service, combining the skills of engineers, divers, and countless others to ensure their operation. So, you see, underwater construction is a complex yet fascinating field. It's a testament to human ingenuity and resilience, a dance of science and engineering performed beneath the waves. The maintenance and repair of these structures represent mankind's endeavor to conquer one of the final frontiers on our planet, the ocean depths. From planning to maintenance, underwater construction is a testament to human ingenuity. This statement captures the heart of a process that's both fascinating and complex. The journey through the intricate process of underwater construction is a journey that truly illustrates the might of engineering and the boundless capacity of human innovation. Water, with its inherent challenges such as currents, pressure, visibility, and corrosion, has been tamed by the human mind to serve the purpose of construction, be it for exploratory, commercial, or transportation purposes. The process starts at the drawing board, with meticulous planning and design, where teams of engineers, architects, and marine biologists brainstorm to overcome the challenges the marine environment poses. They must account for a myriad of factors such as water depth, currents, wave action, soil composition, and seabed topography. Every single detail is deliberated upon, every single possibility mapped out. The purpose of the structure also plays a pivotal role in shaping the design, be it offshore oil rigs, bridges, tunnels, ports, pipelines, or other infrastructures. Each of these structures poses its own unique challenges, requiring different techniques and materials. An oil rig, for example, demands extraordinary resilience to withstand the harsh marine environment, while a tunnel requires immense strength to resist water pressure and avoid collapse. Next, we delve into the initial stage of site preparation, which may involve dredging, leveling the seabed, or even installing temporary structures to create a dry workspace. This is as critical as the construction itself, setting the foundation for the subsequent work. It ensures a stable and safe environment, enabling the smooth functioning of the future steps. We then move towards the construction techniques employed. The role of construction divers is crucial here, as they are the ones who brave the depths and pressure to assemble and install the structures. Equipped with specialized equipment and guided by the planning team above water, they navigate the marine world to physically construct the structures. Remote-operated vehicles, ROVs, also play a pivotal role in situations where human intervention may not be feasible or safe. Controlled from the surface, these autonomous machines can go deeper, stay longer, and perform tasks that may be hazardous or impossible for divers. Prefabricated components form a significant part of underwater construction, as they allow structures to be built in a controlled environment and then transported and installed underwater, risks associated with underwater fabrication. Specialized techniques for concrete placement, such as tremie and pumping methods, are also used to overcome the challenges posed by water, and to ensure the quality of the structures. The choice of materials is another aspect that comes with its own set of challenges. They need to withstand the harsh marine environment, including the corrosive effects of salt water and the immense pressure of water depth. Concrete, steel, fiberglass, and various corrosion-resistant alloys are often used for their resilience and strength. Apart from construction, the maintenance and repair of these structures are equally important. Regular inspections and testing are carried out to ensure the structural integrity of these constructions. Environmental impact assessments are conducted at regular intervals, ensuring the structures are not causing any harm to the marine ecosystem. Lastly, we touch upon the ongoing maintenance and occasional repairs required for these structures, ensuring their continued functionality and safety. Divers and ROVs are sent down periodically for inspections, and any necessary repairs are made then and there. The structures, although built to last, are not immune to the forces of nature and hence need constant monitoring and upkeep. In essence, underwater construction is not just about building structures beneath water. It's about overcoming pushing boundaries, making the impossible possible. It's not just about creating concrete structures. It's about creating symbols of human resilience, perseverance, and innovation. It's a testament to our ability to adapt, innovate, and create. Next time you see an offshore oil rig or drive through a tunnel under a river, remember the marvel of engineering that made it possible. In the fascinating world of underwater construction, one of the most complex and challenging projects is the creation of an underwater road. Let's delve deeper into this intriguing concept. Firstly, a feasibility study is conducted to assess the technical, economic, and environmental viability of the project. Potential routes for the underwater road are evaluated considering factors such as water depth, seabed geology, existing infrastructure, and environmental impact. The alignment and depth of the tunnel sections are planned to minimize underwater construction challenges. Detailed geotechnical surveys are performed to understand seabed conditions, soil types, and geological features along the proposed route. The stability and suitability of the seabed for tunnel construction are assessed. Any potential hazards such as underwater currents, seismic activity, or geological faults are identified. The underwater tunnel sections are designed using specialized software and engineering principles. The dimensions, shape, and materials for the tunnel segments are determined based on the anticipated traffic load, water pressure, and environmental conditions. Features such as ventilation shafts, emergency exits, and drainage systems are incorporated into the tunnel design. An appropriate construction method for building the underwater tunnels is selected, considering factors such as water depth, soil conditions, and project timeline. Strategies for managing construction risks, ensuring worker safety, and minimizing environmental impact during the construction phase are developed. Durable and corrosion-resistant materials for the tunnel segments, such as reinforced concrete, steel, or composite materials, are chosen. Specialized construction techniques for working underwater are implemented. Tasks such as inspection, maintenance, and underwater construction activities are carried out by construction divers and remotely operated vehicles, ROVs. Stringent safety protocols are implemented to protect workers involved in underwater construction operations. Measures to minimize disruption to marine ecosystems, protect marine life, and prevent pollution during construction and operation of the underwater road are put into place. Lastly, a comprehensive maintenance plan for the underwater road is developed. This includes regular inspections, repairs, and corrosion protection measures. Protocols for emergency response and disaster management are established to address potential incidents. Ongoing monitoring and maintenance of ventilation, lighting, drainage, and other essential systems ensure the safe and efficient operation of the underwater road. Building an underwater road using a tunnel system is indeed a complex and challenging undertaking. But with careful planning, innovative engineering solutions, and a strong commitment to safety and environmental stewardship, it is possible to create vital transportation links beneath the waves, connecting communities and facilitating economic development. In the realm of underwater construction, one project stands out as a testament to the marvels of human ingenuity: the Channel Tunnel. This engineering marvel, often referred to as the Chunnel, connects mainland Europe and the United Kingdom through a 31.4 miles, 50.45 kilometers, underwater passage, making it one of the longest underwater sections in the world. In the early planning stages of the Channel Tunnel, multiple proposals were considered, including an artificial island midway for changing horses. However, it wasn't until 1986 that the construction officially began. The planning phase of the Channel Tunnel was, in itself, a mammoth task involving extensive feasibility studies, geotechnical surveys, and meticulous route planning. The construction phase of the Channel Tunnel was fraught with challenges. From dealing with difficult geological conditions to managing groundwater inflows, the project was a testament to overcoming obstacles. The engineers had to navigate through a complex maze of chalk marl, a soft material that posed significant challenges. Innovative solutions were required to ensure the safety and stability of the project. One of the most significant innovations was the use of tunnel boring machines, TBMs, which were specially designed for this project. These machines could cut through the chalk marl while simultaneously lining the tunnel with precast concrete segments. This was a game changer in how the project was executed, allowing for a safer and more efficient construction process. Another challenge was the management of groundwater inflows. The Channel Tunnel's route was primarily through chalk, which is a porous rock, allowing water to flow through it. To manage this, a unique drainage system was designed to handle the water inflows, ensuring the tunnel remained dry and safe for use. The construction of the Channel Tunnel was not just about overcoming challenges, but also about innovation. To deal with the challenging seabed conditions, engineers used a technique called slurry shield tunneling. This method allowed them to control the pressure at the tunnel face, preventing collapses and ensuring worker safety. Today, the operation and maintenance of the Channel Tunnel are as remarkable as its construction. The tunnel operates 24/7, 365 days a year, with trains traveling at high speeds in an environment that is safe, clean, and well-maintained. A comprehensive maintenance plan is followed, which includes regular inspections, repair works, and safety drills. The Channel Tunnel is more than just an underwater road. It is a symbol of human determination, innovation, and engineering prowess. It stands as a testament to what we can achieve when we dare to dream big, plan meticulously, and work collectively towards a common goal. It truly embodies the marvels of underwater construction.